Welcome to this explainer on object-oriented programming in Java. When you first look at code, it can feel incredibly abstract, right? Just a massive wall of text and symbols. But today, we're going to completely change how you see it by turning that abstract code into something highly tangible. We're going to treat Java like a relatable factory production line and break down exactly how software creates, manages, and interacts with virtual objects. Here is our production schedule for today. We'll be moving through the blueprint and the object, anatomy of a Java class, bringing objects to life, methods and data protection, constructors and special keywords, and finally, the Java API toolbox. Let's get right into it. Part 1, the blueprint and the object, from concept to reality. Before we type a single line of code, we really need to wrap our heads around the fundamental philosophy of how Java views the world. In the real world, pretty much everything is an object: a car, a student, a laptop, a bank account. And every single one of those objects has properties, which is its data, and behaviors, which are its functions. In Java, we separate the concept from the reality. A class is simply the blueprint. It outlines those properties and behaviors, but it isn't real yet. You can't open the door of a blueprint house. But an object, that is the actual, tangible, constructed house built from those plans. The class creates the objects. It's the design phase versus the manufacturing phase. Moving to part 2, anatomy of a Java class, structuring our blueprint. Inside a Java class, the anatomy is strict and highly organized. It primarily consists of fields, which are variables declared inside a class. Think of things like an integer for a roll number, a string for a name, or a double for marks. Then we have methods. These are the actions or tasks the object can perform, like study, attend lecture, or submit assignment. And wrapping all of this up, the entire structure is governed by specific data types and access modifiers that dictate exactly how this blueprint is allowed to interact with the rest of the program. Part 3, bringing objects to life, calling in the construction crew. It's honestly fascinating how we transition from a flat, conceptual blueprint into a living, breathing object taking up actual space in our computer's memory. Think of creating an object as issuing a work order. When you type student S equals new student, you are actively hiring a construction crew. Step 1, you define the class type. We're building a student. Step 2, you create an object reference, S, which is basically the name tag or the remote control for our object. Step 3 is the magic word, new. The new keyword tells Java to go allocate actual physical memory space for this specific object. And finally, step 4, we call the constructor to initialize it. And the best part, you can do this over and over again. You can have student 1, student 2, student 3, and each instantiated object gets its very own separate memory space. But how do we pass information around in this factory? Well, when you pass arguments or parameters into methods, Java strictly uses something called pass by value. This is absolutely crucial to remember. It means Java makes a copy of your variable's value and passes that copy to the method. So, if the method changes that value, say it changes x to 100, the original variable back where it started remains completely untouched and unaware. It's kind of like an oblivious bystander. Your original data is completely safe from being accidentally overwritten by a rogue method somewhere else in your code. Part 4, methods and data protection, securing the factory floor. So now that our house is built and functioning, we need to talk about who actually gets the keys to change what's inside. We need to secure the factory floor. If we're dealing with sensitive data, like student grades, bank account balances, or employee salaries, we have to ask ourselves a serious question. How do we keep our data safe from malicious or even just accidental outside interference? Because if anyone can access our marks variable and just change it to whatever they want, our whole system completely falls apart. The answer to that is encapsulation. This is a massive pillar of object-oriented programming. By making our data fields private, they get locked tightly inside the object. We then force everyone to use public getter and setter methods to interact with that data. If someone wants to change a student's marks, they have to go through a setMarks method. This is brilliant because it ensures we can add validation, like checking to make sure the marks aren't a negative number, providing real security and maintainability for our entire application. Part 5, constructors and special keywords, the rules of assembly. Let's step back onto the factory floor for a second to look at the exact moment an object is initialized and the special rules governing its internal environment. When we use that new keyword, we're actually calling a constructor. Constructors are special methods that share the exact same name as the class, and they have no return type whatsoever. They're automatically invoked the very moment the object is created to initialize it. But here's where it gets really powerful. They can be incredibly flexible through a feature called constructor overloading. You can have a default constructor that leaves the object empty, or you can have a parameterized constructor that loads it up with specific information, like a roll number and a name right off the assembly line. Java just looks at the parameters you provide and automatically picks the matching constructor. And we've definitely got to talk about where these variables actually live and breathe in our code. Scope dictates a variable's lifespan and its visibility. Local variables only exist temporarily, completely trapped inside a specific method. Instance variables belong to a single specific object, like one student's individual name. But static variables? Those are a different beast entirely. They are shared globally across the entire class. So if you have a static variable called count, every single student object in your program is looking at and sharing that exact same count variable. Now, what happens when things get a bit crowded inside your methods, and you end up with parameters that have the exact same name as your instance variables? To avoid total confusion, Java gives you a lifesaver, the this keyword. This explicitly points to the exact current object you are working on. So if you write this.id equals ID, you are explicitly telling Java, hey, take the ID parameter I just passed in and assign it to the ID field of this specific object I am currently building. Finally, Part 6, the Java API Toolbox, our pre-built components. The absolute best part about building massive applications in Java is that you don't have to invent every single tool in your factory from scratch. Java provides massive API packages. These packages contain highly optimized, pre-built classes. Need to handle text? Just use the string class. Need to grab user input? Pull in scanner. What if you need complex calculations, random numbers, or dynamic lists? Classes like math, random, ArrayList, and HashMap give you a sprawling warehouse of incredibly reliable, shared code. It vastly accelerates your projects because you aren't stuck reinventing the wheel every time you code. We've toured the entire factory today. We've gone from drawing up conceptual blueprints as classes to allocating memory to construct real objects. We've secured our data tightly through encapsulation, and we've unpacked the massive potential of the Java API Toolbox. Fully understanding these concepts is the absolute key to unlocking the true power of Java development, which leaves us with one final, very exciting question to wrap up this explainer. Now that you have the blueprints, what will you build?